Uh, Thank you. We're going to start the next session here with Tom, who's going to be talking more about early universe physics. So, thank you, Tom.
Thanks very much. I'm going to take it as a compliment that we statistically have the same number of people today as we had yesterday. So thanks for coming back. I realized I'm gonna start with a joke because Simeon did such a great job engaging us with YouTube videos of neutrino mutations, and there were so many interesting and beautiful slides that we saw throughout the day. And I was up half the night trying to find any YouTube video I could on cosmology. There was one Eureka show. There was a sci-fi show called Eureka that had a snippet on a chaotic inflation device, but it's protected by copyright, so I couldn't bring it in. Anyway, so as I said, I really tried to find a joke, and so here it goes. Um, our final speaker yesterday was talking about how you couldn't ever find a horse with two heads. So I decided to ask ChatGPT to give us one. And so here's the horse with two heads. And that's the joke I'm going to start with, which is not nearly as funny to you as it was to me all night. Laurent, do you find it funny? No. Okay. Anyway, machine learning. Anyway, okay. So I want to say that when I was first invited to do this, I had this plan in my mind that we were all going to spend time actually doing a lattice simulation together. Because when we get to the end of inflation, it's actually important for us to go beyond the zero mode, right? And so I had this idea that we would do that we'd all get our laptops out and we would do this full-fledged lattice simulation. And then I did a test run with like 10 people, and it took 6 hours to do. So we're not going to do that today, although I do want to say that everything that I'm going to be talking about in the next 40 minutes are based in some way on these high resolution nonlinear dynamical simulations. And so there is a tutorial, or for lack of a better word, tutorial, on my website where you can download the software that we use, which is called Gabe. I'll talk a little bit more about that later. And there's some instructions that you can use to go through and do this work yourself. And I recommend trying it out, okay? It's actually very popular right now. I've seen lots of papers, for example, that end with, and we're going to put this in the lattice, right? Or we're going to do a cosmolattice simulation, or we're going to do a blah, blah, blah. And so I think it's a great idea before you actually need the tool to go out and do a little practice with it and see what the tools can use. And actually, my second 40 minutes today will be about advice that I have if you choose to do that, because some sizable fraction of you at some point will want to do a nonlinear dynamical simulation. Okay. And like I did yesterday, I want to start with some citations. If you're looking for sort of reviews or overviews of what happens at the end of inflation, these are some of the papers that I look to for help or look to for guidance when I forget what I'm doing, which happens a lot. And so these slides, obviously, you can see the citations when you look back at the recordings. Okay. And I apologize if I'm missing any citations to anybody's work in the room. That's just how it goes. So we were, yesterday we had a good chat about how to get inflation out of a scalar field. We focused mainly on this idea of slow roll inflation, which is the right-hand panel that you see on the slide here. I also alluded to the fact that there are other ways of getting inflation from a scalar field. As long as I have a regime where the energy budget is dominated by potential energy, I get that W equals -1 equation of state, and I get an inflationary period. Even if I have inflation, I have to make inflation end, right? And this is what we used to refer to as the graceful exit problem, pretty much because in the old inflationary models, or if I try to use a pseudo-stable scenario to use, to get my inflationary scenario, if I have something like that and I end inflation through bubble nucleation and collision, I actually end up with a really messy, inhomogeneous universe at the end of inflation. And that's terrible because the whole point of inflation was to make it not bumpy, right? Or to give us the right amount of bumpiness in order to get the structure that we see. And so new inflation or slow roll inflation was a way to get out of inflation without creating those bumps. However, in that case where I have new inflation, I end up with a universe that has no particles in it. I end up in a homogeneous universe where the only fluctuations exist in 1 part in 10 to the fifth, and all of the energy is trapped inside this inflaton field, which, as we saw yesterday, was just homogeneously oscillating about its minimum. Right? It got me out of inflation, but it kept me in an equation of state that didn't give the right conditions to create stuff. Right? And so, if we're going to take an early universe model seriously, yes, it has to solve the problems of Big Bang cosmology, but it also has to let us end in a period that can actually start the universe that we see. Namely, there have to be baryons, and there has to be nuclei, and there have to be things that can eventually become puppies, right? And so the universe has to reheat, right? It has to the stuff that the universe is made of has to transition from inflationary stuff into regular stuff. Now, in QFT, it's really easy to write down interactions that allow one field or one type of particle to decay into another type of particle. If I have those sort of interactions, though, I have to worry about the fact that those interactions can cause corrections to the inflationary potential and ruin the solution to the problem that I started out with. And so it's not exactly clear from the get-go how you're going to be able to take your inflationary model, couple it to something else in a way that doesn't destroy inflation, but also provides a channel to create the hot early universe that we need in order to have a Big Bang. And while there are some scenarios in which so the couplings to other fields have to be really small, and there are some scenarios in which, if inflation happened at a high enough scale, there is still time for our great old QFT perturbative processes to decay into our standard model particles. But if you've been reading some of the inflationary literature, like it's getting much more popular to think about inflation as a lower energy process, in which case a little bit of help is needed. No matter what your feeling is about how inflation might have ended, there is still the argument that the end of inflation provides yet another opportunity to test what physics existed in the early universe. So that's what I'm going to talk about. So I'm going to start by giving the classic sort of prototypical example of what could happen at the end of inflation in a standard model. Not the standard model, but in a regular model. It's something that we now call vanilla preheating, which was the original model of preheating that was developed in the 1990s, which goes a little something like this. So you saw this movie yesterday, where on the left-hand side, I have the homogeneous mode of the inflaton, and on the right-hand side, I have the evolution, the log of the scale factor. So as the inflaton is oscillating about its minimum, it's now coupled to a second field, which I'm going to call the chi field. Right? Again, at a first pass, it's always nice to just call all of our particles are going to be scalars. And I'm going to couple that using a good old-fashioned dimension 4 operator, where the phi field can interact with the chi field in this sort of four-leg interaction. Okay? So I've added a field. I've let them talk to each other. But again, I'm constrained by the fact that if g squared is too big, it's going to ruin inflation. Right? And so I'm in this world where g squared is actually really, really small. And so will I ever, or how do I get the energy out of the inflationary field and into the chi field? Well, the first way to think about this is to actually examine what the dynamics of the chi field are. Right? So the chi field is starting off in some vacuum state. Right? It doesn't have any energy that contributes to the expansion of the universe. However, the Klein-Gordon equation also has a dv chi term. And so there's this extra term now that couples all of the modes of chi to phi squared. Now, phi squared in this scenario is a homogeneously oscillating field, right? It's just going back and forth. And so for the time being, it's not a bad assumption or a bad replacement to take phi and replace it with the expectation value of phi, right? Just so that I have the time-dependent part of the phi field in this term. This is something that maybe looks a little like an approximation, but really it's just rewriting it in a way that helps us to understand that the thing that matters the most to the chi field is the average value of phi, because that's the thing that matters most to the phi field. right? This is looking at the things that are most important to the dynamics of the system. And then I get this fun mode equation for chi. And you say, well, that's interesting, but what can I do with it? Well, the history goes that this equation is actually hiding something beautiful, right? Or this mode equation is hiding some physics that we actually know about. We have to dig a little bit to see it. But it's hiding something that's actually going to help the universe create puppies. Okay. So to understand that, or to give us some intuition for that, so I'm now going to make some approximations in order to think about what's really happening in this system. So in a non-expanding universe, so I take a snapshot now where the time over which I'm considering is small compared to the expansion rate. And in that non-expanding universe sense, I actually know what the dynamics of the phi field look like, right? It's just a homogeneous field in a quadratic minimum. And so the phi field is going to have some amplitude times cosine or sine, right? It's simple harmonic oscillator. Yeah, simple harmonic. Okay, everybody's with me. Yeah. Okay, it's gonna get heavy soon. Okay, I love you. Great. All right, so I'm gonna do a rearrangement because if I take phi and I square it, I can replace it with a 1 minus cosine. I'm doing this coordinate transformation to just rewrite this equation in a way that I can look up in a table of integrals. Okay. So I have a mode equation on the bottom now. I've gotten rid of the Hubble friction term because I'm ignoring the expansion of the universe, and I plugged in for the average value of phi. A now slightly more obscure coordinate transformation can allow me to rewrite one of these constants as something that I'm going to call Q, okay, which is basically proportional to the size of the oscillation of phi and the size of the coupling. And another parameter, A of k, which contains the wave number, and also there's a Q in it. And I end up with this equation on the bottom. Now, I was reminded this morning that this equation, as much as I'm about to say, you all recognize this, but I was reminded this morning, no one has seen this before. I don't know, has anybody seen this before? Okay, yeah. Okay. This is what's known as the Mathieu equation, okay? Which again is something you probably have never heard of before. But what this is an equation for, it's the equation for something with a time-dependent mass. Okay? It's not an external force, but it's a time-dependent mass. And what's neat about having a time-dependent mass is that for certain combinations of A and Q, a time-dependent mass can amplify the size of your mode or not. Okay, so if I do a harmonic oscillator substitution into this equation, I can find that in some cases, solutions to this equation are unstable because again, they have an imaginary part of their frequency, and an imaginary part of the frequency gives you an unstable solution. But the relationship between what is unstable and what is stable is actually a nonlinear problem. And so that's why the Mathieu equation gives us a pretty complex instability diagram, which is plotted on the right, which helps me to find out which values of A and which values of Q have an imaginary part of their characteristic exponent and therefore are unstable solutions. Okay, those are for the math majors in the audience. For the rest of us, what this means is that I'm going to choose some value of K and some value of G squared. I'm going to calculate what the A is and what the Q is, and then I'm going to look at this plot to find out whether or not it lies inside one of these colorful bands where the solution is unstable, or in one of the red regions where the solution is stable. Oh, this is the ansatz you put in to find out where the instabilities occur. So physically what that means is if I choose some value of the coupling, I'm really choosing the value of Q, which means that I'm lying along one of these vertical lines. So I choose some value of Q, right? And I lie along one of these vertical lines. Of course, A of k is k squared over m plus 2q. So that's what the black line is. So I start at the black line and I go all the way up from there. At the black line is k equals 0. Above the black line is k greater than 0. I can take that line. Now let me make it a little bit more intuitive by taking that line, turning it on its side, right? So then rather than plotting the size of the imaginary part of the characteristic exponent through color, I can actually plot the imaginary part of the characteristic exponent by height, okay? Because I only care about that line anyway. So I put that on its side, and I can find that there are two places, on that line at least, where I intersect regions of the instability diagram that have unstable solutions. This is the ah moment. Ah. Okay. So what this means is, from a classical perspective, I have a choice of G, the coupling, and I have a choice of K. I set G by whatever physics I have, and now I vary K starting at the left, where K, starting at the, A K equals 0. And then I go all the way, I'm sorry, that's AK equals 2Q. I go from K equals 0 to K equals infinity. And I find that for some values of K, I have an imaginary part to my characteristic exponent, which means I have an instability band. And then there's actually, this line happens to intersect another little instability band. Yeah. So I was asking why I don't have a choice of phi. And the reason for that is because maybe that was set by whatever the end of inflation looked like in my inflationary model, right? So the work that we did yesterday, that was an uncoupled field, and that sort of set the amplitude of phi, okay? And so, yes, so then, so that kind of, I don't really have a choice there. Now, deep in your question is, well, if I put back on the expansion of the universe, that's going to change. And I'm going to get back to that in a minute, okay? But great question. The physical choices I have for this reheating process are, what can I say about the coupling? And then what modes are excited? Right. And I really think this should be an awe moment, because what it says is that classically, some modes are better than others. Right? Some modes are excited because they're driven by the time-dependent mass that corresponds to the frequency of the homogeneous field. Now, I said that all of you have seen this before. You've played on a swing? Yes? The swings? Okay. All right. You're on a swing. What do? You want to swing higher because that's the most fun. What's the only thing you can change? You can't touch the ground because it's a groundless world. Yeah. Yeah. Go ahead, Dave. Yeah. Yeah, right. You kind of pull yourself up and down, right? You're changing your moment of inertia. You have a time-dependent moment of inertia that takes your swing and it makes it amplified in its motion. There's no external force there. There's work done, but there's no external force. It's merely the change of your moment of inertia that amplifies that mode. And you know from your experience as a kid that if you try to drive it at the wrong frequency, you don't get going. Right? Your mind actually tunes you into the right frequencies. So for certain choices of parameters, you have exponential behavior. You have instability. And for other choices of parameters, you don't. This is a movie that shows what that swinging means for some value of k that exists inside the diagram, where the opening and closing of this parabola is the time-dependent mass of the system. And so you can see you start with a tiny little oscillation. As the time-dependent mass hits the right frequency in time, sometimes the mass just happens to be moving to the left when the thing goes up. That drives it further to the other side. That's what you did on the swing. You just happened to be moving forward and you pulled yourself up. You found the right cadence in order to make that instability happen. So in the physical system, there are actually a countless number of modes, right? Some of them, like the mode on the left, are going to be unstable and are going to be amplified by this process of having the time-dependent mass correspond to whatever the frequency of the mode is. Some of them, like the mode on the right, are going to be out of sync. And therefore, there will be no unstable solution. That's equivalent to being in one of those red areas from the Mecce instability diagram. Again, because of Simeon, I put in perhaps another beautiful example of this is the old Tacoma Narrows Bridge.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear.
This is the wind, is the homogeneous mode of the inflaton.
The center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now.
And the wind is causing the puppies to get excited.
There's an automobile caught on the heaving road.
You guys can see this video?
The 11,000-ton center span twists and...
Stop there. Okay. And so anyway, all of that was to try to convince you, because you all seem really convinced, that having dynamics like this, or just having that normal coupling, the very first thing you'd write down in QFT, even for small values of the coupling parameter, give us regions of K space, that is values of K for which I have true instability from a purely classical standpoint. As the inflaton is oscillating about its minimum, it will be connected to other fields, and those other fields will have instabilities for only certain values of K. Right? And therefore will produce particles given a, oh, should I? You can keep going. Okay, right. So that's the intuition. Now back to Io's question, right, is now of course everything that I've said is sort of perfect in this non-expanding universe sense. Okay? And in order to do the problem, right, you have to think about it in terms of, well, at this instant, these are the bands that are excited and these are the modes that aren't excited. But once the expansion of the universe comes into play, those instants change. For this oscillation, there might be this band that gets excited. For this oscillation, there might be this band that gets excited. As the amplitude of the field goes down, I move from one value of Q to another value of Q. And so there's some tools that we can try to do to describe this. So one is called flow K analysis, where again, I have to take some, I have to make some assumption about the shape of the oscillating homogeneous mode. But already my instability diagram went from those, sort of horizontal looking instability bands to now these curved instability bands, because I'm starting to include more important terms relevant to the dynamics of the system. Now that's fine, but this is still only good for some short period of time around which I'm doing the flow K analysis. And so what's better than doing flow K analysis? Just doing the problem. Right? We know that these instability bands exist, right? We know that given some amplitude and given some coupling, I know that there are going to be solutions for which certain values of K are excited, and I can actually generate inhomogeneities and particles and all the things that we love in the universe. But I can't really do the precise prediction beyond knowing that the effect exists. Right? Maybe I could do it for an oscillation, or maybe I could do it for a specific delta t, but I can't do it in its entirety. And so I want to convince you that it's actually a good idea to take the system when you can, right, and actually solve the system. Because after all of these approximations that I did came from this set of coupled differential equations, which for somebody with a simple mind like me can say, I understand what these are doing, and why don't I just solve them in order to find out what the physics looks like? So Klein-Gordon equations plus the Hubble constraint equals happiness, right? And so this is what the simulations actually look like, right? So this is the same vanilla preheating scenario, but now I'm not going to make any assumptions about the amplitude of phi. I do have to set what g squared is in order to do the simulation. But what you're going to see on the left-hand side is you're going to see the value of the homogeneous field of phi, and that's a time-dependent statement. Now I'm doing a two-dimensional slice, so the horizontal axis is the homogeneous value of phi. On the right-hand side, I have the chi field. Right? This starts off at 0. It has a little bit of fluctuations in it because, again, these fields are great things to quantize, and so I can give them Bunch-Davies initial conditions. And what we're going to see is that the homogeneous motion of phi is going to induce these instabilities in the chi field that we see on the right-hand side. Again, if you take those links that I showed you, you can do this simulation in about 5 minutes on your laptop at home. Right? I guess back in the day, it used to take us a week on a big computer, but now maybe you could even run it on your phone. On the bottom, just so that we can tie it into the stuff that we were talking about before, the left-hand plot on the bottom shows the homogeneous value of phi, which, of course, as Io points out, changes over time, right, because it decays. And on the right-hand side, I'm plotting the variance of the fields, which is something we'll come back to a couple of times, because the variance is a notion of how bumpy the field is. Right? So the bigger the variance, the more the variance grows, the more the field deviates from its homogeneous value, and therefore, in a sense, the more particles are created and the hotter the universe is. Anyway, the movie speaks 1,000 words, right? It's oscillating up and down. I can't see it yet, but my modes of chi are feeling that instability, right? But they started off really small, so even exponentially growing is going to take a moment. There's going to be a minute, maybe right now, where chi actually starts to look much more like a drum head, right, than noise. There it is. And we know that this sort of characteristic standing wave, Lev Kaufman always used to say this characteristic standing wave is really an indication that this is a non-thermal process, that there's only a single value of k that's important. There's one mode, right? Much like in a tuning fork, right? There's one mode that's most important that's giving me the dynamic, that's showing me that this really is that instability band, that there really is a section of k that becomes important and that grows exponentially. But that doesn't last for long in nonlinear physics, because those particles now can scatter off phi particles and create a soup, and at the end of the day, end up in some stage that's ready to thermalize and that's ready to produce everything that we need from Big Bang nucleosynthesis. And what's outstanding is that this problem happens really fast, right? This happened over a couple of, I don't know, 12 or 15 oscillations of the field. Right? Whereas if I waited in this model for the phi field to decay through sort of perturbative processes, I'd be waiting many, many, many e-foldings. And so this gives us a beautiful, hot, spicy universe quickly using physics that was present in the problem that we might have missed if we were thinking about the problem as purely a homogeneous one. It's also something that we might have missed if we stuck to just flow K analysis, because it turns out, as you can see from the variances here, there actually are a lot of stages of this process where I have some stages where I can trust the linearized approximation of the flow K analysis, but then there are stages where it's purely nonlinear, right? Where all of the interactions come from higher order terms, and I can't linearize the problem about some known solution. And so the resonance happens first, where my modes of chi are being amplified. You can see that the red line is going up, but the black line isn't. Then this beautiful stage where the created particles interact with each other, and then eventually those interactions cause the background of the phi field to decay, which I've rescaled the oscillations of the phi field to show that it decays relative to the regular expanding universe system. Should pause for questions. Have I convinced you? The universe gets warm. Yeah.
So you said that there's only one mode that matters in the end. Is that true for all kinds of models where you can choose your potential for the inflaton to be whatever you want?
So let me rephrase it just in case I said it imprecisely. So when the resonance is happening, it looks like there's one mode that's most important, right? But that doesn't mean that the process is dominated by that one mode, right? So especially in the movie that I showed, where I have the phi field is really just a sine omega t, right? There's the harmonicity of the field, if that's a word, really drives a band in the chi field. If I have models of inflation where the behavior of the inflaton at the end of inflation is more complex, then that's going to mix up these instability diagrams, maybe have more bands, maybe have other types of bands, right? And so the procedure can get much more rich and much more complicated the more I add to the system. And I think this undergirds the fact that like the flow K analysis, as beautiful it is for producing our intuition of the existence of instability modes, it's not really the test to see whether or not those instability modes evolve into a preheated universe, into a reheated universe. Great question.
I had one other question.
Yeah, go for it.
So in this preheating phase, what type of observable could we be looking for to determine if we're looking for the right thing or not? My first guess would be probably maybe a gravitational wave, because on the electromagnetic spectrum, I don't see that we could.
Yeah, so I have like 5 slides dedicated to that.
Okay.
So do you mind waiting for just a minute? And then if I don't answer it, I'll point back at you.
Okay,
or if I answer it, if I think I'll get back to you. Yeah.
That's fine.
Oh.
So the literature talks about both reheating and preheating.
Great. Okay. Yeah. So great. So Fred asked, like, what is the difference? So my title was reheating, and now the entire time I've been talking about this nonlinear process. So why is this different, or why is this a subset of reheating? Well, reheating is the process by which I really get the universe into a thermal phase at a temperature higher than 5 MeV. Right? If this didn't happen, the universe we see today would not exist. Right? So if inflation occurred or ectorosis, if anything happened in the early universe, it had to create a universe that was at that temperature with a thermal spectrum, which is, of course, the only way I can say that it has that temperature. That's reheating. Now, to get a thermal spectrum, all I really need is some energy in some modes and some nonlinear operator that allows energy to go between those modes, right? So that the modes are connected to each other. What preheating is, right, is it's a way to use nonlinear physics to get the energy out of the phi field in a way that is perhaps efficient, right? So a nonlinear process that gets out of the energy out of the phi field for, as our last question asks, specific modes. And why specific modes is important is because that means that the distribution of energy that I get from preheating is not a thermal distribution, but energy in those modes plus the nonlinear terms that I have will eventually lead to a thermal distribution. It's actually one of the most interesting things that we're tackling right now is, can these lattice simulations ever even give us a thermal spectrum or not, right? And that's something I won't talk about, but I will allude to it at some point. Great. Other questions? Because I have lots of other slides, but I really want to make, like, this is the point of what I want to say today, right? And so before I give other examples, I want to make sure we haven't moved on too fast. It's way in the back, but okay.
Hi, great talk so far. I had a quick question about the assumed form of the Lagrangian that you mentioned towards the beginning.
Yeah.
So first question is there any sort of real restrictions on G or G squared in the sense, like, do you want it to be perturbative? Do you want it to, like, could G itself be imaginary and then G squared be negative? Like,
okay, so if you couldn't hear the question, it was like, what's up with your interaction term, right? What do we know about G squared? Now, in the old days, G squared was positive, right? And which is why we wrote it as G squared, right? So that we would have, so that the potential would be bound from below at all points. People have gone beyond that. Actually, there was a time when we set G squared to be negative. The real physical limit on G squared is that it doesn't screw up the inflationary potential. So there are loop corrections to the potential that occur because of that interaction. And if that G squared is too big, then it's going to ruin the predictions of inflation.
Okay, and just one more question following up. So in the Lagrangian, you didn't, or at least I didn't see a mass term for this chi field.
Yes. I'll get back to that.
Okay.
Okay.
Cool.
That's a lot. I hope to talk about.
Cool. Okay. Yeah. I will follow up if. Cool. Thanks.
Thank you very much. Yeah. And there was one more, maybe. Yeah.
Yeah. So when you're talking about you get this one band of K modes that are in resonance, right? You have this non-thermal distribution. that comes about, and then it thermalizes. Thermalizes with what is kind of.
Well, so what it with itself, right? So so okay, this is kind of tied to the last question. If the mass of chi is very small, right, then that's really why I don't include it here, is because we just assume that the mass of chi is much smaller than the mass of phi. But that makes the modes that I'm exciting in chi ultra-relativistic, okay, which gives them an equation of state of a third, as Simeon pointed out. I think as Simeon mentioned that I said correctly, right? Yeah, that I can get an equation of equation of state of 1/3 out of having ultra-relativistic modes. So as the spectrum goes from having these peaks in it, where I had instability bands, to an evolved spectrum where they're allowed to talk to each other and therefore thermalize, I get a continuous spectrum that I would want to match with some Boltzmann distribution to say that's what the temperature is. But it's totally fine because that is of itself radiation. And that gives me my radiation-dominated universe.
So you mean like a phi field with just one mode is only going to have one K band, but like you're saying, a more complex.
Well, no, even that will then lead to this thermalization process, because once it becomes nonlinear, those modes all talk to each other.
Okay.
Right? And that's when the transition from preheating to reheating happens.
Okay, I see. So even with one.
Yeah.
Okay.
Great.
Thank you.
It's beautiful. I mean, of course I would say that. I've spent my whole life doing it. Okay. I'm about 40 minutes behind. There are a lot of models. You could do it with fermions, tachyons, Palatini-Higgs, non-minimal terms, blah, 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 even with deep learning, right? So there are the process that I'm telling you about, and I am going to give you some more examples if we can find another 40-minute slot for me. There are lots of places where we've discovered that by doing the problem, we have found places where instability bands occur. And the existence of these instability bands, or the existence of preheating in these scenarios, is something that just happens because of the model, and it's something that we can't really avoid. Okay? And it's something that we really have to understand. Maybe I'll say this, and then we'll take the break, and then I'll try to reorient myself to get the next two talks into 40 minutes. But of course, from a dynamical standpoint, all of this boils down to understanding what the effective mass of the modes looks like. Right? So if I'm going to have modes that are unstable, that instability has to come from the fact that specific modes experience some sort of resonant process that allows those modes to grow exponentially. I've already described the mechanism by which parametric resonance happens, right? The swinging on a straight swing resonance, where I have a time dependence in my effective mass that causes, for certain frequencies, I have excitation. But I can also have, as I do if I let g squared be negative, I can have scenarios where the effective mass itself is negative, right? Which is what we call a tachyonic instability. Because when the effective mass is negative, the only solution to the harmonic oscillator in those cases is the growing mode. Right? And so there's a regime now, there are many models in which a negative effective mass can lead to the amplification of a certain set of modes. And those actually usually happen very, very quickly and at somewhat lower values of K. There's nothing wrong with these because, again, my understanding of this mode as being tachyonic is one that's based in perturbation theory. So once the system becomes nonlinear and the background of phi breaks down, what I thought was a tachyonic mode turns out to be just a plain old regular mode. Right? And so all of these things are ways of us to see why these instabilities exist, why certain modes grow exponentially, and that can lead to eventually a reheated state. So we'll pause there for 10 minutes. I'll rename my slides. We'll talk about observables, and then give a couple of examples, and then lessons from cosmology. So see you in 10, but don't be late because I really have a lot of slides to go over.